The surface tension of soap solution is 30 dyne per centimeter. A soap bubble made from this solution has a radius of 1 centimeter. The work done in doubling the radius of the soap bubble is, here are the following options. Now, for a soap bubble, we multiply the area by 2 since there are two free surfaces. Therefore, the surface tension T is given by dW upon dA, where dW is the work done and dA is the area. Therefore, we need to find out the value of dW, which is the work done, which is equal to 2 into dA. And since there are two free surfaces, we multiply the area into 2. Therefore, we get T into 4 pi into 4r square minus r square into 2, which is equal to 24 pi r square T. Therefore, now the work done will be 24 pi r square T. Now substitute the values of everything. We get 24 into 3.142 into 1 square into 30, which is 2262 ergs. Therefore, here the correct answer will be option B. Work done in blowing a soap bubble of 10 centimeter radius is, here the surface tension of the soap bubble is given as 3 by 10 Newton per meter. Now, well, it is 75.36 into 10 raised to minus 4 joules, or 75.36 joules, or 37.68 into 10 raised to minus 4 joules, or 150.72 into 10 raised to minus 4 joules. Now, the work done is given by the formula W is equal to 8 pi TR square. We need to find the work done. Therefore, 8 into pi is 3.14. The surface tension is given as 3 upon 100, and the radius is given as 10 centimeter, which is 10 raised to minus 1 the whole square. Therefore, on calculating everything, we'll get the answer as 75.36 into 10 raised to minus 4 joules. Therefore, here the correct answer will be option A. A wire 10 centimeter long is placed horizontally on the surface of water. It is generally pulled up with a force of 1.4 into 10 raised to minus 2 newtons. To keep it in equilibrium, the surface tension of water is, here are the options. Now we all know that the tension is given by the formula T is equal to F upon 2L. Now here it is generally pulled with the force. The force is 1.4 into 10 raised to minus 2 newtons upon 2L. Now for water, L will be 2 into 10 raised to minus 2. Therefore, on calculating, we get the answer as 0.07 Newton per meter, which is equal to 70 dyne per centimeter. Therefore, the correct answer here is option C. Liquid rises in the capillary tube up to a height of 6 centimeter. If the area of the cross section of the tube is made 1/4, then the water will rise in the tube up to a height of A 3 centimeter, B 1.5 centimeter, C 12 centimeter, or D 24 centimeter. Now, H, we know that H is inversely proportional to 1 by R. Therefore, area is made 1 upon 4th. Hence, R will be halved. R will be halved since H is inversely proportional to 1 by R. Therefore, H will be doubled. If the liquid, therefore H will be doubled when the area of the cross section of the tube is made 1/4. Therefore, since original H was 6 centimeter, the new H will become 12 centimeter. Therefore, the correct answer is option C. Water rises up to a height 10 centimeter in a capillary tube. It will rise to a height which is much more than 10 centimeter if the apparatus is kept either on the surface of the moon in a lift moving up with an acceleration at the North Pole on the equator. Now the height up to which the water rises is given by the formula H is equal to 2T upon R into rho into G. So we can say that H is inversely proportional to 1 by G, inversely proportional to G, where G is the gravitational force, which is in meter per second square. Now we know that on the surface of the earth, G is always the same anywhere. So in option B, C and D, as the apparatus is kept on earth, it will be same for every G. However, when when we are on the surface of the moon, the g decreases significantly, which leads to an increase in height. Therefore, the answer here will be option A, because on moon there is no gravity. Therefore, the correct answer is option A. Two capillary tubes of the same diameter are kept vertically in two liquids whose densities are in the ratio 4 is to 3. What is the ratio of the heights h1 upon h2 in the two capillary tubes if the surface tensions are in the ratio of 6 is to 5? Assume that the angles of contact are equal. Now, let the ratio of the surface tension T1 upon T2 be equal to H1 rho 1 G1 upon H2 rho 2 and G2. Therefore, H1 upon H2 will be T1 rho 2 upon T2 rho 1. Therefore, H1 upon H2, we know the ratios of the tension and the rho. Therefore, we substitute the values, we'll get 6 upon 5 into 3 by 4, which is equal to 9 by 10. Therefore, here the correct answer will be option B. A 20 centimeter long capillary tube is dipped in water. The water rises up to 8 centimeter in the tube. If the entire arrangement is kept in a freely falling elevator, the length of the water column in the tube will be A 4 centimeter, B 10 centimeter, C 16 centimeter, and D 20 centimeter. Now we know that H is inversely proportional to G. Therefore, if the acceleration due to gravity decreases, h will increase. Now, this arrangement is kept in a freely falling elevator. Therefore, here g is equal to 0. Therefore, h is basically infinity. But it rises to the full length. Therefore, here the correct answer will be 8 centimeter, 20 centimeter. The correct answer is option D. 1,000 small water droplets of equal size combine to form a big droplet. The ratio of the final surface energy to the initial surface energy of the water droplets are 1 is to 1,000, 10 is to 1, 1 is to 10, or 1,000 is to 1. Now, 4 upon 3 pi r cube, this is the volume of the big drop, is equal to 1,000 into 4 upon 3 pi small r cube. Therefore, capital R cube is equal to 1000 R cube. Therefore, R is equal to 10R. Therefore, now E1 will be equal to 1000 into T into 4 pi small r square, and E2 will be equal to T into 4 pi into 10R the whole square. Therefore, E2 upon E1 will be equal to 100 r square upon 1000 r square, which is 1 is to 10. Therefore, the correct answer is option C. The radii of two mercury drops are R1 and R2 under isothermal conditions. A drop is formed from them. The radius R of the resultant drop is given by, here are the options. Now, since the radii are given R1 and R2, therefore 4 upon 3 pi r cube, this is the volume of the resultant drop, will be equal to the sum of the volumes of both the drops, which is r1 cube plus r2 cube. Therefore, r cube will be equal to r1 cube plus r2 cube. Therefore, this is the answer. Therefore, the correct answer from all the options is option C. Two narrow tubes of diameter 30 mm and 60 mm are joined together to form a U-shaped tube open at both ends. If the U-tube contains water, what is the difference in water levels in the two limbs of the U-tube? Surface tension of water at the temperature of the experiment is 7.5 into 10 h 2 minus 2 Newton per meter. Take the angle of contact to be 0 and density of water to be 1.0 into 10 h 3 kg per meter cube, and take G as 10 meter per second square. Now let H1 and H2 be the heights up to which the water rises in the two limbs of the U-tube. Then H1 is equal to 2t cos theta upon R1 rho g, and H2 is equal to 2t cos theta upon R2 rho g. R1 is equal to 1.5 into 10 raised to minus 3 meters, and R2 is equal to 3 into 10 raised to minus 3 meters. Now because R1 is less than R2, H1 is more than H2. Now for water, theta is equal to 0 degrees. Therefore cos theta is equal to 1. Therefore H1 is minus H2 is equal to 2T upon rho g is 1 upon R1 minus 1 upon R2, which is equal to 15 into 10 raised to minus 3, 3 minus 1.5 upon 3 into 1.5, which is equal to 5 into 10 raised to minus 3 meters, which is 5 millimeters. Therefore, here the correct answer will be option B. The lower end of a glass capillary tube is dipped in water. Water rises to a height of 8 centimeter. The tube is then broken at the height of 6 centimeter. Then the height of the water column and the angle of contact will be, here are the options. Now when the capillary tube is broken at the height of 6 centimeter, the height of the water column will be only 6 centimeter. So the height of the water column is 6 centimeter. Now to calculate the angle of contact, now because tension is equal to R into H into rho g upon 2 cos theta, therefore H will be equal to 2T cos theta upon R rho g. Therefore H upon cos theta is equal to 2T upon R rho g, which is a constant. Therefore H1 cos theta 1 is equal to H2 cos theta 2. 8 upon cos 0 is equal to 6 upon cos theta 2. Therefore, cos theta 2 is equal to 6 upon 8, which is 3 upon 4. Therefore, theta 2 is equal to cos inverse of 3 upon 4. Therefore, the correct answer here will be option D, 6 centimeter, and cos inverse of 3 upon 4. The lower end of a capillary tube of radius r centimeter is placed vertically in water. What is the heat evolved if water rises up to a height h in the capillary tube? Now surface tension T is given by 2h rho g upon 2 cos theta, which is equal to rhg upon 2 cos theta. Now for water, rho is equal to 1. The upward force due to surface tension will be s 2 pi r into t cos theta. Therefore, the average work done in lifting the water through a height h, W will be 2 pi r t cos theta into h upon 2. We consider the average height to be h by 2. Therefore, W will be equal to 2 pi, which is equal to pi r into rhg upon 2 cos theta into h, which is equal to pi r square h square g upon 2. But W is equal to J into H. Therefore, the heat evolved will be equal to W upon J, which is equal to pi R square H square G upon 2J. Therefore, the correct answer will be option D. A metallic wire of length L and density D floats horizontally on the surface of water. What should be the maximum radius of the wire so that the wire will not sink in water? Here are the options. Now, the force due to surface tension will be equal to the weight of the wire. Therefore, 2TL will be equal to pi r square L dg. Therefore, r square is equal to 2T upon pi dg. Therefore, r is equal to root of 2T upon pi dg. Therefore, here the correct answer will be option C. A capillary tube of radius small r is immersed in water and water rises in it up to a height h. The mass of water lifted in the capillary tube is 5 grams. Another capillary tube of radius 2r is immersed in water. What is the mass of water that will rise in the second tube? Now here are the options. Now let's take T dash is equal to 2h rho g upon 2 cos theta. Now for water we know theta is 0 degrees and cos theta, cos of 0 is 1. Therefore H is equal to 2T upon R into rho into G. Now the mass of water that is lifted in the capillary tube is M is equal to pi R square H rho, which is equal to pi R square rho into 2T upon R rho G, which is equal to 2 pi T upon G into R. Thus, mass is directly proportional to R. Therefore, m dash upon m will be equal to R dash upon R, which is 2. Therefore, m dash is equal to 2m. Therefore, m dash is equal to 10 grams. Therefore, here the correct answer will be option B. A soap bubble assumes a spherical surface, which under the following statement is wrong. Now we can look at the statement one by one. Now the first statement says that the soap bubble encloses air inside it, which is actually true. That is what a soap bubble does. So the first statement is true. Now then the second statement, it says that the soap film consists of two surface layers of molecules back to back, which is true. When you dip something into into a soap solution, it encloses twice the layers. Therefore, that is true. Now, in the third statement, the pressure of air inside the bubble is less than the atmospheric pressure. Hence, the atmospheric pressure compresses it equally from all sides to give it a spherical shape. Now, this is not true. The pressure inside the soap bubble is more than that of the atmospheric pressure. Therefore, the excessive pressure is given by the formula 4T upon R. Therefore, option C is actually wrong. Now, so this is the wrong option. Therefore, the correct answer here is option C. Option D is also correct because of the elastic property of the film. It tends to shrink, which is correct, to a small surface. If excessive pressure inside a soap bubble is balanced by oil column of height 2 millimeters, then the surface tension of soap solution will be 3.9, 3.9 into 10 raised to minus 2, 3.9 into 10 raised to minus 3 Newton per meters, or 3.9 dyne per meter. Your R is given as 1 centimeter and density D as 0.8 grams per cc. Now the excessive pressure is given by 4T upon R, which is equal to h into density into the acceleration due to gravity. Therefore, the tension will be given by R into h into d into g upon 4. Therefore, substituting the values, we'll get 10 raised to minus 2 into 2 into 10 raised to minus 3 into 0.8 into 10 raised to minus 10 raised to 3 into 9.8 upon 4, which is equal to 3.9 into 10 raised to minus 2 Newton per meter. Therefore, here the correct answer will be option B. Pressure inside a small air bubble of radius 0.1 millimeter situated just below the surface of water will be equal to, here are the options. Now the surface tension of water is 17 to 10 to minus 3 Newton per meter, and atmospheric pressure is 1.013 into 10 to 5 Newton per meter square. Now the excessive pressure inside the air bubble is given by 2T upon R. Therefore, P in minus P out, pressure inside minus the pressure outside, is equal to 2T upon R, which is equal to 2 into 70 into 10 raised to minus 3 upon 0.1 into 10 raised to minus 3, which is 1400 pascals. Now, therefore, P in will be equal to 1400 plus 1.013 into 10 raised to 5, which is equal to 1.07 into 10 raised to 5 pascals. Therefore, here the correct answer will be 1.027. Sorry, this is 1.027. 1.027 into 10 raised to 5, which is option C. Pressure inside two soap bubbles are 1.01 and 1.02 atmospheres. Ratio between their volumes is, here are the options. Now, outside pressure is 1 atmosphere. Now, the pressure inside the first bubble is equal to 1.01 atmosphere. Therefore, the pressure inside the second bubble is equal to 1.02 atmosphere. Therefore, the excessive pressure is equal to 1.01 minus 1, which is 0.01 atmosphere. This is excessive pressure 1, and the excessive pressure 2 equal to 1.02 minus 1, which is equal to 0.02 atmosphere. Now, the excessive pressure, change in pressure, is inversely proportional to R. Therefore, R is inversely proportional to the change in pressure. Therefore, R1 upon R2 will be delta P1 upon delta P2. Delta P2 upon delta P1, which will be equal to 0.02 upon 0.01, which is 2 by 1. Now, since V is equal to 4 by 3 pi R cube, therefore V1 upon V2 will be equal to R1 upon R2 the whole cube, which is 8 by 1. Therefore, here the correct answer will be option C. Excessive pressure inside one soap bubble is 3 times that inside a second soap bubble. Then ratio of the surface area is 1 is to 9, 1 is to 3, 3 is to 1, 1 is to 27 or 9 is to 1. Now the excessive pressure inside a soap bubble P is given by 40 upon R. Therefore, P1 upon P2 is equal to R2 upon R1. Now it is given that the excessive pressure inside one soap bubble is 3 times that inside the second soap bubble. Therefore, P is equal to 3P. Therefore, 3P upon P is equal to R2 upon R1, which gives R1 upon R2 is equal to 1 by 3. Therefore, the surface area, the ratio of the surface area S1 upon S2 will be 4 pi R1 square upon 4 pi R2 square, which is 1 upon 9. Therefore, the correct answer here is 1 is to 9, which is option A. 8,000 identical water drops are combined to form a big drop. Then ratio of the final surface energy to the initial energy of all the drops together is 1 is to 10, 1 is to 15, 1 is to 20 or 1 is to 25. Now as the volume remains constant, R cube, capital R cube is equal to 8,000 into the small r cube. Therefore capital R is equal to 20R. Therefore the surface energy of one big drop upon the surface energy upon 8,000 small drops will be equal to 4 pi r cube t upon 8,000 4 pi small r square t, which is equal to r square upon 8,000 r square, which is 20 r square, the whole square upon 8,000 r square, which is 1 upon 20. Therefore the correct answer is option C, 1 is to 20. Work done in increasing the size of a soap film from 10 into 6 centimeter to 10 into 11 centimeter is 3 into 10 raised to minus 4 joules. The surface tension of the film is, here are the options. Now the work done is given by the formula W is equal to T into the area. Therefore T is equal to W upon delta area. T is equal to 3 into 10 raised to minus 4 upon 2 into 110 minus 60 into 10 minus 10 raised to minus 4. Soap film has two surfaces, therefore it is multiplied by 2. Therefore, on calculating this, the answer will be 3 into 10 raised to minus 2 Newton per meter. Therefore, here the correct answer will be option B. 1,000 small water drops of equal radii combine to form a big drop. The ratio of the final surface energy to the total initial surface energy is 1000 is to 1, 1 is to 1000, 10 is to 1 or 1 is to 10. Now as the volume remains constant, therefore the radius of the big drop is equal to n raised to 1 by 3 into the radius of the small drop. Therefore the surface energy of one drop, big drop, upon the surface energy of n drops is equal to 4 pi capital R square T upon n into 4 pi small r square T, which is equal to capital R square upon n small r square, which is equal to n raised to 2 by 3 r square upon n r square, which is equal to 1 upon n raised to 1 by 3, which is equal to 1 upon 1000 raised to 1 by 3, which is equal to 1 up 1 is to 10. Therefore the correct answer here is option D. A liquid drop of diameter d breaks up into 27 small drops of equal size. If the surface of the liquid is sigma, then change in the surface energy is, here are the options. Now the work done here is given by 4 pi capital R square T n raised to 1 by 3 minus 1, which is equal to 4 pi capital D upon 2 the whole square into sigma n raised to 1 by 3 minus 1, which is equal to pi d square sigma 27 raised to 1 by 3 minus 1, which is equal to 2 pi d square sigma. This will be the change in the surface energy, which is option B. The surface tension of water is 7 into 10 raised to minus 2 Newton per meter square. and its contact angle of contact with glass is 0, the rise of water in a capillary tube of diameter 0.5 millimeter is A 10 centimeter, B 8 centimeter, C 5.7 centimeter, and D 4 centimeter. Now we know that H is equal to 2t cos theta upon r into rho into g. But theta for water is 0, therefore cos 0 is equal to 1. Therefore H is equal to 2t upon r into rho into g. Upon substituting the values of t, r, rho and g, we'll get the answer as 5.7 centimeters. Therefore the correct answer is option C. A liquid rises to a height of 3.3 centimeter in a capillary tube of radius small r. If the radius of the capillary tube is made 0.75 r, then the height to which the liquid will rise in the capillary is. Here are the options. Now, we know that the height is inversely proportional to the radius. Therefore, h1 upon h2 will be r2 upon r1. Therefore, h2 will be equal to h1 r1 upon r2, which will be equal to 3.3 into r upon 0.75 into r, which is equal to 4.4 centimeter. Therefore here the correct answer is 4.4 centimeter, which is option C. 10 centimeter long wire is placed horizontally on the surface of a liquid and is gently pulled up with a force of 2 into 10 raised to minus 2 newtons to keep the wire in equilibrium. The surface tension of the liquid in Newton per meter is 0.002, 0.001, 0.2 or 0.1. Now the surface tension is given by the formula T is equal to the force upon the length. Therefore the force given here is 2 into 10 raised to minus 2 upon the length, which is 2 into 0.1, which is equal to 10 raised to minus 1 Newton per meter, which is equal to 0.1 Newton per meter. Therefore the correct answer here is option D. Water rises in the capillary tube to a certain height such that the upward force due to the surface tension is balanced by 75 into 10 raised to minus 4 Newton force due to the weight of the liquid. If the surface tension of water is 6 into 10 raised to minus 2 Newton per meter, the inner circumference of the capillary must be. Here are the options. Now, the surface tension into the circumference will be is equal to force. This is the general formula. Therefore, we can find the circumference by dividing force by the tension, which is equal to 75 into 10 raised to minus 4 upon 6 into 10 raised to minus 2, which will be equal to 12.5 into 10 raised to minus 2 meters. Therefore here the correct answer will be option D. Capillary tube of radius r is immersed in water and water rises in it to a height h. Mass of the water in the capillary tube is m. If the radius of the tube is doubled, mass of water that will rise in the capillary tube will now be m, 2m, m by 2 or 4m. Now mass of the liquid in the capillary tube is given by m is equal to pi r square h into rho. Therefore we can say that m is directly proportional to r square into 1 by r, as h is directly inversely proportional to 1 by r. Therefore we write 1 by r in place of h. Therefore m will be directly proportional to r. Therefore if radius or r is doubled, then mass will also become double. Therefore here the correct answer will be option B, 2m. A soap bubble is blown by using a mechanical pump at the mouth of a tube. The pump produces a certain increase per minute in the volume of the bubble, irrespective of its internal pressure. Which one of the following graphs correctly represents the relation between excessive pressure inside the air bubble and the time? Here are the graphs. Now we know that the excessive pressure is given by the formula delta P is equal to 4T upon R. Therefore we can say that the excessive pressure is inversely proportional to R. Now, as the radius of the soap bubble increases with time, therefore we can say that delta P is inversely proportional to T. That is, if time decreases, delta P will increase. Also, like if time increases, delta P will decrease. So, in here, graph C perfectly shows the relationship between P and time, pressure and time. Therefore, C is the correct option. Of the following graphs represent the variation of surface tension of water with temperature for a small range of temperatures. Here are the different graphs. Now, which one of them may be correct? Now, for small temperature differences, the variation in the surface tension with temperature is linear. For small temperature differences, for small differences, and is given by the formula Tt is equal to T0 into 1 minus alpha T, where Tt and T0 are the surface tension at T degrees Celsius and 0 degrees Celsius respectively, and alpha is the temperature coefficient of surface tension, and the surface tension decreases with increasing temperature. So now the surface tension decreases with increasing temperature. Therefore, graph C is the correct option, which shows that as the temperature increases, surface tension decreases. Therefore, C is the correct option.